So today's video is going to be looking at a pretty basic equation that tells us a lot about a pretty complex concept. So the equation here, delta S is equal to Q over T. Q is still kind of heat energy, or sometimes it's shown as like change in heat energy, over temperature. And once again, sometimes you'll see that as like average temperature. That equals this delta S here, or the change in entropy. So entropy is kind of a pretty complicated concept um, with some pretty easy definitions. I know that's kind of contradictory. The best way to think about entropy is it's kind of disorder. Whether we're talking about energies, atoms, stuff like that, the universe tends to want these things to be completely jumbled up and disordered. And we know that from like the three laws of thermodynamics. The third law specifically, or the second law, I should say, um, that some energy is always lost as entropy. Entropy must increase every time we have a change in energy somewhere. That increase in entropy is either going to be within the system or within the surroundings. When we look at refrigeration, we're really creating order within the refrigerator. We're separating it into there's a place that's cooler and a place that's warmer. That's order. And we know that it takes a lot of energy to, create that cooler compartment within the refrigerator. And we can actually see, the outside of the refrigerator gets warmer. There's an exchange of heat taking place. In fact, the outside gets warmer more than the inside gets cooler, and that's because of things like friction, stuff like that. So let's actually take this equation and let's actually put it to use. So down there at the bottom of the screen, we have this question: a 125 gram chunk of ice at the temperature of 0 degrees Celsius absorbs the thermal energy from its surroundings to melt into water. We want to calculate the change in entropy. Well, based upon the blah blah, the change of entropy equation, I need heat energy and I need temperature. All right, so in this case, the heat energy isn't given to me into the question, but temperature is. In this case, the temperature, by the way, for this, I will need to convert into Kelvin. To do that, you just find Kelvin. You just take your degrees Celsius and add 273.15 to it. It's easy enough conversion, um, but we're going to get there. All right, so I have T. I don't have Q, but if you remember back when we were looking at latent heat, we know that Q is equal to the mass of the substance times the latent heat of either fusion or vaporization. In this case, I'm talking about melting. I'm talking about the latent heat of fusion there. And we can actually calculate this out right away. I know that the ice has a mass of 125 grams. And if I go through and I check my list of latent heats, the latent heat of fusion of water is 334 joules per gram. Okay, so take that times 334 joules per gram. And that number you would just get from a table that lists different latent heats of fusion or vaporization. So I have 125 times 334. Can't do that one in my head. And can't evidently get my, there it is. Nope. Go through it the old way. There we go. All right, so I've got 125 times 334. That gives me 41,750. Bring it over quick. 41,750. 41,750 joules. All right. So that's my joules. That's my Q. And I know from that question, T is equal to 0 degrees Celsius. So to convert it into Kelvin, I'm going to add 273.15 to it. And in fact, that's all I'm going to end up with, 273.15 Kelvin. So now I'm going to take my Q. If change in entropy is equal to Q over T, we have 41,750 750 joules over 273.15 Kelvin. That's easy enough to do. That number's there, divided by 273.15. I get 152.85. 152.85. Now my unit in this case is going to be joules per Kelvin. It's kind of a weird unit. Um, really, we just kind of know how much energy is essentially being lost or disordered to per Kelvin kind of change in temp. It's not great, but the equation by itself is pretty easy to use. I know I messed a lot up with this video, so please feel free to tell me about it. Um, but yeah, so that's kind of how you calculate change in entropy. Like I said, it's basic. It's a three equation one. It's just the hard part is sometimes finding your Q uh, because you're gonna have to go back, maybe do like use Q equals MC delta T, and then you're gonna use the average temperature. Sometimes you got to figure out, the heat using latent heat stuff. Finding Q, I think, is probably the toughest part about this equation here, because you can't really find Q without those. But that's it. That's kind of a basic short video kind of go through that, but I hope it helps.